So I thought I'd start by saying a few more words about air conditioning and the context of the broader context, partly responding to some of the questions that I've talked about with people about the problem set, because I view the problem set that was just due as just sort of filled with public service aspects, like things that actually will be valuable to you to know, literally valuable. It can save you money on your heating bill, and more broadly society. This is controlling our energy consumption is useful. So about air conditioners and heat pumps in general, in this mild climate Virginia's got a relatively mild climate as say compared to Canada, places or Antarctica. Moving heat around here strategically using devices that air conditioners and its friends is a very effective way of heating and cooling your house at essentially minimal consumption of ordered energy. So the real issue that I have in mind is what are known as heat pumps. That those of you who live in Virginia, particularly live in separate housing in Virginia, you probably have a heat pump or one or more heat pumps in your house, and you just think of these maybe as the air conditioner and the heater, but they are a sophisticated device that acts as an air conditioner during the summer and as a heat pump, which I'll define more carefully in a minute, during the winter. What's the idea? That you can move heat. This is the whole story. The story I've been telling you about air conditioners is it is possible to move heat against the natural flow. That is, from a cold object to a hot object. That's not the way nature had in mind. That act by itself increases the order of the world. Equivalently, decreases the disorder of the world, decreases the entropy of the world. You can't do it. You cannot move heat from cold to hot and nothing else, because that would lower the total entropy of the world. It would violate the law of entropy. It's statistically forbidden. It just never would happen. Okay? But if you're willing to consume ordered energy, as in electricity, and convert it into disordered energy, thermal energy, enough to create enough additional entropy to compensate for the ordering effect, you can do this. And that's what heat pumps and air conditioners do. They move heat the wrong way. They can't do that as the only thing they do. They also have to consume ordered energy and convert it to thermal energy in such a way that they create the additional entropy necessary to be sure that the entropy doesn't decrease, and in fact always increases in real situations. Okay? So when you're air conditioning your house, the air conditioner is absorbing heat from the indoor air where it's cold, an act which orders that cold air significantly, because cold air is very sensitive to thermal energy. Its entropy changes significantly, a lot, let's say, when you add or subtract heat to a cold object. You then take that heat outside where it's hot, and you drop off that same heat. Well, hot objects are less sensitive to thermal energy. Their entropy doesn't change as much. So you've lowered the entropy of the cold thing a lot. You then drop off the thermal energy outside, and you increase the entropy of the hot thing a little. There's a drop in entropy. That's forbidden. So how do you pull it off? You create additional entropy outside by turning electrical energy into thermal energy and dropping it off outside as well. You don't just sort of like do this because the tax season shows up and it says, well, you're behind on your entropy, and so you got to go make some. It's fundamentally built into the act of pumping heat from cold to hot. So you remove 1 unit of heat, for example, from inside where it's cold, and you drop off more than 1 unit of heat outside where it's hot. The extra heat used to be electric energy. So far we're on board? Questions about this so far? That's air conditioning, and that's really the only way of cooling your house. You can't just lower the temperature of the house with no other consequences. You have to move heat around. To heat your house, you have a couple choices, and I'll describe the heat pump first, and then I'll show you my newspaper pieces. To heat your house, you got the two classic choices are what's known as a space heater. The space heater is just one of these electric devices you plug into the wall. They come in lots of shapes and forms. They're all effectively equivalent to a toaster. They have a device that takes electrical energy and just crushes it into thermal energy. Nothing else. They are all inherently 100% efficient. If you buy 1,000 joules of electric energy from the power company, you end up with 1,000 joules of thermal energy in the house. No more, no less. Perfect. 100%. But you can actually do better. Use the second scheme. The second scheme is to run what's called a heat pump, which is just an air conditioner run backwards. What it does, so this is during winter. You're trying to heat your house. It's cold outside. You want to make your house warm. That means you want to deposit thermal energy in your house. And after years of just running a space heater where you buy 1,000 joules of energy from the electric company and you create 1,000 joules of heat, you're thinking, well, maybe I can do something better. And something better is the observation that the great outdoors is, even though it's cold out there, there's lots of thermal energy out there. There's no shortage of thermal energy. And all these years we talk about energy crises and energy shortages and stuff. There's no shortage of energy. Energy's everywhere. It's just most of it's thermal. And you can't work with it. It's tough. It's disordered, and it doesn't do what you want it to do anymore. In this case, okay, so there's lots of thermal energy around outside. The trick is to carry it inside. How do you do that? You run an air conditioner backwards. You have the cooling unit outside where it gathers thermal energy from the outdoors and makes the outdoors colder, which seems kind of goofy, but no one's out there, in fact, no one's out there. They don't mind. So you're cooling the great outdoors, and you carry the heat inside and release it in the hot end, what would normally be the throwaway part of an air conditioner. An air conditioner throws the heat outside where no one cares about it. Here now you're throwing away the heat inside where you do care about it. And the heat that you pump from outside to inside is joined by additional heat that came from where? Well, it used to be electric energy from the power company. The act of pumping the heat consumed electric energy because, and it has to, because you got to make sure that overall the entropy of the world doesn't decrease. So pumping it required the creation of additional entropy by turning electric energy into thermal energy. And that additional thermal energy shows up inside as well. So for example, just to give it some substance, I guess, suppose you're trying to put 10,000 joules of thermal energy in your house. Two choices. One, run a space heater. Buy 10,000 joules of electric energy from the power company, turn it into 10,000 joules of thermal energy in your house, toast you warm. And then you go and pay the bill at the end of the month, and it's big. Alternative, run the heat pump. And the heat pump, in my little story, the heat pump gathers 9,000 joules of thermal energy from outdoors, where it's free and plentiful, carries it indoors, and drops it off indoors. Now, that pumping from a cold outdoors to hot indoors isn't for free. Thermodynamics requires the consumption of some ordered energy. How much? Well, let's say 1,000 joules of electric energy. So you buy 1,000 joules of electric energy to convey 9,000 inside. And the 1,000 that you bought from the power company isn't gone. It becomes thermal energy, and you dump it inside as well. Overall, 10,000 joules of thermal energy shows up inside just as before, and it's toasty warm. The difference is you only bought 1,000 joules from the power company. The other 9,000 came from outside, carried in by that 1,000 joules. You okay with this? Questions about this idea? And this is sort of the central issue, and the public service announcement part of this. These devices save energy, not thermal energy. They save ordered energy, which is the only energy that's expensive. Thermal energy is free everywhere. Is that okay? So the reason we use heat pumps here in a place like Virginia is because the temperature difference between outside and inside is never all that large. It rarely gets really, really cold outside. and you usually don't want to heat your house to 120 degrees Fahrenheit. Pretend you're in the desert. No. The result is carrying heat from cold to hot becomes more costly as the temperature difference increases. So if you're carrying heat from just mild cool outside to slightly warm inside, that's easy. That act by itself doesn't reduce the overall entropy much. A little bit. You're ordering the cold one a little more than you're messing up the hot one. But the difference isn't substantial, and as a result, it's relatively efficient to move it. You don't have to use very much ordered energy. The bigger the temperature difference gets, when it's bitter cold outside and you really want hot inside, moving every joule of heat now takes more electric energy. You're fighting a bigger, the law of entropy is really pounding on you now, because the act of moving a joule of heat from very cold to very hot, that's a big ordering effect, and you really have to pay through the nose for it. Okay? So, getting back to just in general, if you want to heat your house in a mild climate like this, where the pumping process is not all that energy expensive, you can save a lot of energy, that is ordered energy, and money, because more energy costs money, and the environment and everything else, if anybody cares anymore, by using a heat pump rather than a space heater. So you understand what a space heater is? It's just, yeah, it's 100% efficient, but that's all. You can do better. You can leverage the energy. So having gone over that harangue, so I've got these. At this point, I found two of these. These are advertisements that start showing up in the local paper about this time every year, or approximately every year. And this is Eden Pure reopens Ohio factory, creates 250 new jobs. How it works. Never be cold again. How it works. Bottom line, these are space heaters. They are just glorified ones with all kinds of fancy selling. How it works. Electricity ignites powerful Sylvania infrared lamp. The quartz infrared lamp gently warms the patented copper heating chambers. The soft heat rides the humidity in the room and provides blah, 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 blah. This one has these pictures of people who look, well, they have quaint beards and stuff and look like they are from another era. It's all sales hype. I figured they're probably just good old boys that just stuck on, done up by the costume company. And they're carrying public rush to snap up new low-cost appliance that helps slash heating bills. Miracle heater, whatever, hybrid thermic, modern marvel. What these ones don't have, and some of the other ones I've seen, 100% efficient. That's all they are, space heaters. They plug into your wall, and they do all this, turning the electric energy into thermal energy and setting it in the room. Big deal. Okay? You might as well just go down to Walmart or whatever your favorite store is and buy the cheapest space heater that's there if you want to do this. It will just turn your electricity right into thermal energy, and things will get warm. You'll be paying a lot of money for it. It slashes heating bills, right? You can just turn off all the heat and walk around in an electric blanket. That'll slash your heating bills. Okay? You understand the issues, and you know, okay, so my heat pumps. Okay. One other thing to talk about before leaving this is perpetual motion machines. Is the term familiar to some of you guys? Perpetual motion machine? Not terribly. Over the years, people keep inventing sources basically of free energy. Perpetual motion machines is a little bit of a misnomer. The idea is basically something that delivers, in fact, ordered energy for free, some way or other. And for me, over the years, I've been contacted by some series of people who either are hawking their latest perpetual motion machine, free energy machine, or having seen advertisements for one are wondering whether they should invest or purchase. The answer is no. And here's why. The free energy, various forms of free energy that come around, they're trying to sell you free ordered energy. And there are one of two origins of that free ordered energy. either thin air, in which case they violate the law of conservation of energy, and are they're absolutely forbidden because they're creating energy out of nothing. And those are known as perpetual motion machines of the first kind. And the second kind of perpetual motion machine provides an endless stream of ordered energy and takes as its input thermal energy. Those don't violate the law of conservation of energy. Energy in, energy out, it's balanced. What they violate is the law of entropy. They're turning disordered energy into ordered energy. And they're known as perpetual motion machines of the second kind. And believe it or not, they just keep showing up. People have successfully patented them. So I was interacting at one point a couple years ago with a guy who had successfully patented one. He had videos of his machine in operation and all that stuff. And it sort of came down to one of these. Well, and there's a little thing a little glitch we're still working on. Little glitch you're still working. And that was the problem. I told him first off that it's not going to work, and second off that this kind of device exists as an unrelated different device already. He was furious then somebody had already stolen his patent, or was already violating his patent. Anyway, he finally took the stuff down, the video down and all that. It went away. But for fundamental reasons, you cannot do this. You cannot turn ordered energy in disordered energy into ordered energy with no other consequences. So the order is going to come from somewhere else. So basically, you're going to be just rearranging things. You're not actually generating original energy. That was this guy's problem. Was actually he had ordered energy entering his system from what he thought was just a trivial some switches in his system. No, those weren't trivial at all. That was how the ordered energy was entering, and that's all he could get out the other end. He thought with a little adjustment he could get out tons out the other end. Nope, no more than he put in. All right, yeah. Wind turbines, where the energy comes from in those. The wind turbine takes as its source of energy the kinetic energy of the wind. So the air, which is ordered. The air's movement. So this is a very valuable question in there. You see that the wind's movement from place to place is ordered because it's coherent. The whole blob of air is moving together. It can do work, and it does do work on the turbine blades. And the turbine blades are wings. It's running a propeller backwards. There's all the airflow over under the wing and the high pressure and low pressure. It's all there, and it makes the wind turbine turn, and therefore does work, rotary work. So it's force times distance is linear work. Rotary work is actually torque times angle. As you twist something and it moves a distance, moves an angle in the direction of your torque, you do work. So, but the energy was work all, by the time it was in the moving air, it was already equivalent to work, right? Ordered energy. Where did that ordered energy come from? It came from thermal. It started as a difference in temperature, for example, between the hot land heated by the sun this morning and the cooler water, which is harder to heat and maintains more constant temperature. So as the sun rises, the land heats faster than the water heats. You get a hot spot and a cold spot. That has order to it, difference in temperature. So what happens, over the hot region, it's a little bit oversimplified, but over the hot region, the air is heated, it rises, lifted by buoyancy. There's a big cycle, and it goes all the way to the top of the atmosphere, so it's a little more complicated. But the air rises over the hot region and descends over the cold region to compensate and flows in from the cold to the hot. That's the wind. Where did it get its ordered? Because now when it's moving, it's ordered energy. Where did it get the ordered energy from? From allowing heat to flow. The cool water is actually being warmed by this process, and the hot land is being cooled by this process. The hot land being cooled is more obvious because air is flowing from the cold surface of the water over to the hot surface of the land and cooling it off. Okay, so you can see the heat's flowing from hot to cold. That process by itself, heat flowing from hot to cold, creates entropy, a lot of it. So it is possible, without violating the law of entropy, to divert some of that thermal energy and turn it into work. And that's what the wind does. It sidetracks some of that thermal energy and makes work out of it. And then the wind turbines generate electricity on this. At night, the winds tend to be onshore in the morning and offshore at night. When the sun sets, the land cools off faster, and now the winds blow the other way, from land to offshore. It's something worth knowing if you're ever floating around in a boat and you lose your paddles, and during the morning it's safer because you get blown towards shore. During the evening it's not so safe because you get blown away from shore. Okay, just as a general rule. But can you see how there is heat flow in here? And it's consuming the order that was present in having a hot thing and a cold thing. And it is in this context of letting heat flow from hot to cold, it becomes possible to create a little work out of thermal energy, to seemingly do the miracle of reordering it. You're not really reordering it. You're consuming order from something else, the heat of the high temperature of the hot thing and the cold temperature of the cold thing. You're ruining that differentiation, and therefore killing off that order, but you get some work out as a result. That is known as a heat engine. It's the opposite of a heat pump, and it is the topic of the day. Okay? So there are lots of heat pumps in heat engines in our world, many of them natural. And automobiles, is not natural, but automobiles are heat engines, at least the current crop. The fully electric ones, that's a whole other story. And if and when there are ones that operate off of what are known as fuel cells, that will also be different. Fuel cells are devices that basically act like batteries. They take chemical potential energy in a fuel, and they turn it directly into electricity. They don't burn the fuel. Burning the fuel creates a lot of entropy right off the bat, and you're immediately having trouble now turning that thermal energy into work. Fuel cells don't do the burning, therefore they don't face this struggle of trying to get useful work out of thermal energy. What's holding up fuel cells is they're really hard to do. To use fuels that aren't super special, to use just ordinary fuels, the fuel cells, either they have to run at high temperature, so you have to start your car and then wait 15 minutes, or they only last a few days, or you need a fuel cell the size of a planet to operate a car. It's just all not very. So it's an area of modern development in science and technology and engineering. Okay, so I talked then at great length about heat pumps. Heat pumps move heat from cold to hot, that is against its natural direction flow, and in doing so they consume ordered energy. They're required to do the pumping. Heat engines do the reverse. They allow heat to flow the way it loves to go, from hot to cold, and they divert some of that thermal energy, that heat, and turn it into work. And that's the story of the specific example is the automobile engine. Wind is a perfectly good example as well. Okay, so opening question then related to this observation is a car burns gasoline to obtain energy, but allows some heat to escape into the air, right? The hot air comes off and stuff. You open it up after you stop and it's all hot. Could a perfect gasoline burning car, not a fuel cell car, when it burns the gas, avoid releasing any heat into the environment? You okay with the question? How many think yes, a perfect car could do that? No heat out in the world. How many think no, wouldn't work? You're right, no it is. They can't do it because the engine operates not by turning thermal energy directly into work. That violates the 100% from thermal energy to 100% ordered energy, electricity or mechanical work. That violates the law of entropy. What they're doing instead is letting heat flow from hot to cold, from the hot burn gas to the cold outdoor air, and they're diverting a substantial fraction of it and turning that into work. Ideally on cars, just to tell you in advance, I think an ideal car burning gasoline could approach about 50%. Give or take 50% of the thermal energy produced by burning the fuel could become mechanical work. The other 50% has to be released as heat. In practice, I think a real car only gets about 25%. So if you buy 1 million joules of chemical potential energy in the form of gasoline, you get about 250,000 of mechanical work out of it. The rest goes out into the environment as thermal energy. All right, so observations like automobiles, because they burn gas for their power. They burn it in a confined space. That's the internal combustion engine. They're rated in horsepower and by volume, and their engines contain cylinders. All these things we'll deal with it shortly. Electrical systems. I used to talk about electrical systems years and years ago, but it's really sort of off topic in dealing with heat. And finally, we've already seen they're propelled by their wheels. They have some wheels that turn as the car moves, so-called free wheels, and then they have the cars that are powered by the engine and propel the car, and those are the powered wheels. So the questions, these 6 questions that I'll go after, the first one is the most in-your-face one, is how does the automobile manage to run on thermal energy? How does it pull out? Mostly I've talked about thermal energy as being kind of useless. And the answer is that it's a heat engine. And before I let too much time go by, let me show you 2 heat engines, one pretty obvious and one a little more subtle. So this is the obvious one. This is a little toy steam engine. Yeah. So what I just did is I lit a little natural gas burner in here, which is going to heat a pot of water up here. So this can here has water in it. In case I can zoom in for a second, although we'll get stuck on it forever. I don't remember that. So remind me to come back. So now you're looking at this little steam engine, just a little toy guy. The water will get hotter and hotter. We're adding heat to it. Its temperature rises naturally as it's liquid water, just becoming hotter and hotter liquid water. Eventually, we'll get to there's a little evaporation off the top, but because the whole thing's confined, that sort of dies down as the humidity builds up above it. But eventually, we'll get to the boiling point of the water, and we'll actually start making pressurized steam. And we'll have gaseous water that's at higher than atmospheric pressure, and it will flow through a system where that high pressure steam will be able to do work on a surface, push it, and cause it to, it'll push it, the surface will move. It's a piston and cylinder thing. The piston will move. You will have work done on it by the steam. And even though the steam's only source of energy only type of energy is thermal, it can do work. And it does work, and it will get this little guy going. It always takes a while to get up to running. But for it to continue to operate, the heat has to flow out of the hot boiling water and the hot steam into the room air. If you get rid of either one of those, the hot object or the cold object, it'll grind to a halt. It needs the movement of heat from hot to cold to continue to work. Things related to steam engines. Actually, steam engine-like devices power a lot of our utilities. You might think, whether it's gas-fired, coal-fired, hopefully not too much, fuel oil-fired, nuclear-powered, all these electric generating plants, are there any exceptions? Virtually no exceptions. They boil water. They make high-pressure steam. The high-pressure steam then does work on a surface. It may not be a piston and a cylinder. It may be a turbine. Most of them these days are turbines, which are very sophisticated equivalents of a wind turbine. And the heat goes from hot to cold through the turbine, does work on it, generates electricity, and at the end you still end up with hot stuff and waste heat, and that has to be dumped out in the environment. So the cooling towers that you see associated with power plants, or the fact that power plants are often built by bodies of water, they're all dealing with the excess waste heat, the heat they cannot use because they need to run heat. They're heat engines. They're taking energy. They're taking thermal energy from hot to cold. They have to dump some into the cold, and That's what the cooling towers are. These are familiar to you, right? The cooling towers, they often look like, they're big. They're not cylinders because they're shaped aerodynamically because they have airflow issues they're dealing with, which we could also do. I hope you can see that. Like the physics we've done this semester, it shows up all over the place. Okay, I'm starting to hear boiling going on here. We're almost there, okay? Oh, keep going. You can do it. The pressure's gradually building up. Call AAA. There we go. When it's really boiling hard, it goes like crazy, and then it's irritating. Right now it's going slowly, so it's irritating. I guess there's no middle ground. But this is how choo-choos used to run, right? The old steam engines, same device. They're heat engines. They're taking heat from the hot burned coal, and they're dumping out into the great outdoors and diverting some of it as work. Is that all you're going to do? Pretty wimpy. I'll turn off the camera on it, and it'll probably go into high gear. I want to show you the other heat engine we've got here. Dippy Duck. Chug it. I think I can. You still have the little engine that could? Is that around still? Yeah. Okay. Now prove me wrong. Okay, I'm going to stop. Ha. I turn off your source of heat. It stops. Ha ha. So Dippy Duck. How does Dippy Duck here work? Dippy Duck, every time he dips in the water, his head, which is kind of like a stocking cap, gets wet. And as it gets wet in this relatively dry air of this room, evaporation is favored over condensation. So the water begins to evaporate off his head. So far, it's familiar, I hope. And in evaporating, each water molecule that evaporates has to gather more than its fair share of thermal energy from its environment. And as a result, Dippy Duck's head is cold. It's the coldest thing in this room. It is cooled by evaporation, just as your hand would be cooled by evaporation if you spilled water on it. Is that okay with everybody? So it's cold. Dippy's tail is room temperature. And there's a fluid in Dippy's body that evaporates where it's warm and condenses where it's cold. So that fluid is condensing in his head and evaporating in his tail. And as it evaporates in his tail, it pushes a column of the liquid in the fluid up toward his head where it's condensing. Can you see that fluid rising? It's no longer visible now. It'll be visible in a minute. So the fluid keeps rising up in his head, toward his head, from the bottom towards his head, until he tips over, in which case the fluid pours down the edge of the tube, and it starts over. So the fluid is now mostly in his tail, and it's rising. See it go up to the top? It's evaporating the bottom, condensing the top. So he's getting top heavy. As the fluid rises up, he's going out of balance. He's going from a stable equilibrium. Boy, everything repeats, right? He's going from a stable equilibrium to an unstable equilibrium, and he tips over. And then he dips, and then he spills, the fluid falls back down to his tail, and then starts to rise again. So he'll keep busy with this until it runs out of water. He is a heat engine. That is, all this movement you see in him, which conceivably could do work. You could do work with a duck that's wobbling back and forth like this. It's kind of not a lot of work. You have to have really low expectations. But it originated as thermal energy in the temperature difference between his butt and his head. And that difference in temperature between his butt and his head originated as a different form of order. It originated in the order that's present in a glass full of water and a room that has relatively dry air. This, I hope, is familiar to you. That system, all the water in a cup, not much water in the air, that's orderly. It's a lot more orderly than all the water spread every which way in the room and the cup empty. So Dippy is consuming the order that is present in the fact that we've got all the water in this, most of the water in this room is all confined to this cup. We're undoing that ordering. Dippy is using that to create a temperature difference between his head and his tail, and then he's consuming the energy, the order that's in that temperature difference to make himself move. Every time one of these cycles occurs, it warms his head up, it undoes the cooling, and it cools his tail down. So he's basically order is working its way through the system until finally it's destroyed completely. Is that okay? Are you follow the ideas those ideas? Questions about it, whatever. All right. So an automobile is the same thing. An automobile has heat flowing from the hot burn gas to the cold outside air. You divert some of it, turns it into mechanical. The overall entropy of the world goes up as a consequence, despite the fact that some of the thermal energy has been converted into mechanical work to propel the car. I've already talked this one to death, so that one too. Go. Okay. So how efficient can the automobile be? In principle, the bigger the temperature difference between the hot object and the cold object, the larger the fraction of the thermal energy making the trip you can convert into ordered energy. So this comes about for reasons I've talked about in the context of air conditioners. I'll remind you the air conditioner one. If you move heat from a cold object to a hot object, you order the cold object more than you disorder the hot object. There's a net reduction in entropy that you got to pay for. And the bigger the temperature difference is, the bigger the reduction in entropy you got to pay for. Because it's really cold, taking a dose of energy out, thermal energy out of it, really orders it a lot. And if it's really hot, adding a dose of thermal energy to it disorders it a tiny bit. Okay? So bigger temperature differences, harder to pump. Heat engines is the reverse, or something, one of those converse, inverse, bozo versus universe. If you let heat flow the way it wants to go from a hot object to a cold object and divert some of it as work, the bigger the temperature difference is, the more entropy this transfer will produce. Because you let heat flow from a really hot object where taking away a dose of thermal energy doesn't do anything to ordering it, and you dump it into a really cold object where that dose of thermal energy creates a humongous amount of thermal energy, of entropy. There's a gigantic spike in entropy. That will cover a lot of sins. So you can divert a big fraction of the thermal energy that was making the trip and turn it into work and not violate the law of entropy. So as the temperature difference becomes bigger between the hot object that's the source of the heat and the cold object that's the destination of the heat, you can sidetrack more of it. So in principle, the hotter you burn the fuel, so the temperature of the burned gas produced by the fire inside of an internal combustion engine, the higher that temperature. And the colder the place you dump the heat, namely the great outdoors, on a cold day in principle, the engine becomes more efficient. The more of that thermal energy you can divert and turn into work. So in principle, these engines become more efficient when you burn the fuel hotter and you're driving in colder weather. Therefore, one of the quests of all these heat engines, which includes like jet engines and stuff, you want to burn the fuel as hot as you possibly can, subject to limits of the system you're working with. You can't have it melt, for example, or explode. I mean, unless you're trying to set the record. Ha we did it. It exploded, but we set the record. All right. I've talked about everything here except the last subheading, or how the engine pulls this off. So nearly all cars operate, but the only exception is RX-7 still run a rotary engine. But nearly every car on the road that is not pure electric So even the ones that are hybrid, they have an internal combustion engine, and internal combustion engines typically operate in 4 separate steps or strokes. The basic structure they're going to be working with is what's known as a piston and cylinder. So it's a metal can that's open at one end and a plug that moves in and out of that can. And it's going to move in or out 4 times to complete a cycle, a full operating cycle. And those 4 steps, and I'm going to show them to you in a second in detail, have, just to name them, the first one is called the induction stroke. Its job is to fill the empty space formed between that cylinder, that is the can, and the plug. The plug will be coming out of that cylinder and leaving a void in the middle. And we're filling it with a mixture of fuel and air, fuel being typically gasoline and air. And ideally, the gasoline is not a liquid anymore. It becomes vapor. It's gaseous. So they actually want to fill it with, they want to fill that void with a gas that is a mixture of gasoline and air. And that is a potent mixture when you light it, okay? But they don't light it yet. They go to the compression stroke first. The compression stroke, again, works with this piston or plug in the cylinder, and now it pushes the piston into the cylinder and squeezes the gas, this gas being a mixture of fuel and air. And we'll see what happens with that. That's the compression stroke, makes perfectly good sense. There is a moment between this compression stroke and the power stroke at which time the spark plug fires and ignites the fuel-air mixture, which burns extremely quickly to form very hot, high-pressure gas. And now the power stroke happens. In the power stroke, the piston comes out of the cylinder, and in this stroke, that hot, high-pressure gas does work on the piston. It pushes the piston out by way of pressure, and the piston moves a distance in the direction of the push. That's work. And that is what powers the car. The last stroke, the exhaust stroke, once again returns the piston into the cylinder and squeezes out the burned gas and gets rid of it and prepares for the next induction stroke. Is this okay so far? Yes. I'll ask anyway, even if nobody ever says anything. All right, rarely. So here now up close and personal, those 4 strokes. So this is really going on in your car when you start the engine. The pistons and cylinders are going through these cycles. I don't believe there are any cars on the road that have only a single cylinder and piston. They typically have a group of them. We'll see why you need that. The minimum group is 3 maybe. 4 is probably more common. So you may have like a 4-cylinder engine. Has 4 of these babies in there. 6-cylinder, 6 of them obviously. 8, and if you're up into the 12 and stuff, you're basically driving some Bugatti $1 million car, fine. They're around, but okay. So what's going on? In each one of them is going through this sequence. So this is the induction stroke, the one in which you put fuel and air mixture into the cylinder. So here's the cylinder drawn out here. The top is actually a closed or closable structure. It's complicated. It's got valves up there. It's not just simply the end of the can. The bottom is open. It's actually not open to air. It's usually, there's oil in here. This is the oil that you change when you go in for an oil change. This area is all full of oil. So, but this is the business region, right in here where it's painted blue. And during this part of the story, a valve opens at the end of the cylinder to allow things to come and go. In this case, they come. The engine is introducing air and fuel into the cylinder. It puts the air in just the old-fashioned way, letting it flow from high pressure to low pressure. The air comes out of some air filter at a pressure that is higher than the pressure inside this empty space, and so it flows in very easily. At the same time, they squirt in, I guess it's not drawn in here, they squirt in gasoline under very high pressure with what is known as a fuel injector. So it used to be that cars would advertise that they have fuel injectors because it was novel. This was 30 years ago, when most cars used a different way of getting the fuel in.
Now they all have fuel injectors, so it's like boring. So it squirts, it shoots a jet of gasoline into the air rushing into the cylinder, and the gasoline just evaporates essentially instantly. So as this piston comes out of the cylinder, that void fills up with a mixture of gaseous fuel and air. You okay with that? At the end of the induction stroke, this intake valve closes, and the cylinder is now sealed. Nothing can go in or out. And the compression stroke starts. And during the compression stroke, the piston is pushed into the gas, squeezing it, doing work on it, incidentally. This process consumes energy from the engine. The engine has to shove that piston in hard, and that energy has to come from somewhere. This is part of the reason why cars have more than one cylinder, because some of these steps take a lot of work. And the engine doesn't want to be busy doing work on cylinders with no help, with no source of energy. So it's nice to have another cylinder providing work at the same time this one is consuming it. So back to this cylinder. It's doing work on the gas, squishing the bejeebers out of it till it's very high density. It's incidentally also hot. The work becomes heat. The work that you do when you crush this gas together, you know, the gas is being pushed inward as it moves inward. It's having work done on it. That energy doesn't disappear. It remains in the gas. It becomes higher thermal energy in that gas. The gas gets hot, not because of friction, but because of compression. I showed you that the other day with that jug I had up here. As I squeezed gas into the jug with the bicycle pump, it got hotter. Remember that? Has to happen. So the gas gets hot. When it hits maximum compression, they light it. The spark plug fires up there. This guy right here. Fires, poof. The gas burns in a jiffy. At that point, we enter the power stroke, during which time this extremely high pressure gas. Now, it's way more pressure than it had before because the molecules are all traveling faster. They're hitting harder. They're actually also smaller, so that the burning process created smaller molecules. They are now actually way up in pressure as a result. And the piston now gets shoved out very hard. Lots of work done on it. And that work powers the car. The last stage is simple. And that is just, they open the other valve, the exhaust valve on the cylinder, and squeeze out the burned gas and the waste heat and go back and do this again. All over. That's the 4 strokes in a conventional internal combustion engine. You okay with that? Yeah. How does the octane of the gas? Glad you asked that question. I got 2 demonstrations to do. I can just barely pull them off. The first one is, what's the point of the octane? The point of the octane is this. It has almost no effect on the power provided. So there's no reason to have high octane gas. I'll harangue on this next time too. The only reason you have high octane gas is to avoid a problem that occurs during the compression stroke. When you compress that fuel and air mixture, its temperature increases. It threatens to ignite all by itself. And high octane gas holds off the self-ignition, pre-ignition better. I'll show you the pre-ignition. So I'm going to look at this little cylinder down here. And to do that, docking camera. So here it is. We're going to be looking at that cylinder. There it is. You're looking at the bottom of it. And I'm going to put in one little piece of paper in the bottom. There it is, a piece of paper at the bottom. And that by itself, there's nothing to light it on fire. How am I going to possibly ignite that piece of paper? Well, I'm going to do it by compressing air. So I'm going to do work on air by compressing it, just as the engine does work on the fuel and air mixture by compressing it. And the temperature is going to rise so high that it's going to ignite the paper. Ready? Get set. Oop. That wasn't friction. That was the act of compressing the air so violently that it burst the paper burst into flame. You understand the physics of that? This is how diesel engines work. Diesel engines compress the fuel and air mixture. They compress pure air, and then it gets so hot that when they shoot fuel into it, after compressing it, the fuel bursts into flames. In a conventional gasoline engine, though, you don't want this to happen because this means the fuel and air mixture ignite before you're ready for it, before the spark plug fires. So to prevent this process, to prevent compression for igniting the fuel, in certain engines, you use special gasoline that's hard to light. But okay, so my first public, I'll do the other demonstration tomorrow. I'll just harangue you once. Those of you who are buying premium gasoline for your cars that do not require it, that do not exhibit this pre-ignition or knocking, it's called. You can hear this when it occurs in your car. It sounds like marbles rattling around in your engine. Okay? You don't really want it. It's not horrible. It shows up mostly when you're driving up a steep hill and you're really flooring it. If your car doesn't do that much, whatever gas you're using is fine. So most cars on the road today can take regular. Putting the high-octane gasoline in just transfers money from your pocket to the gasoline companies and nothing else, okay? The only point of those fancy gasolines is there are a few high-performance cars that use high-compression engines. They smash the bejeebers out of the fuel and air, and they cause pre-ignition. Otherwise, forget it. Don't use it, okay? On Friday.